Hello, good morning, good afternoon, or good evening. Thanks for taking time out of your busy schedules, everyone, to join us today for a webinar presented by Park Systems. I'm Gerald Pasquale. I'm with the technical marketing team here at the Santa Clara office, and we are very fortunate today to have our application scientist, Dr. Wenqing Shi, from our Albany office in New York, online to give you guys a presentation on PinPoint Piezoelectric Force Microscopy. This is PFM. So if you haven't joined us for a Park Systems webinar before, please be advised that this webinar is being recorded and a recording of this talk will be uploaded to the Park Systems YouTube channel in about 1 or 2 weeks time or so with some minor edits. And it'll be available for you, your colleagues, or even your students, if you're in academia, to review on demand as a YouTube video. You might have noticed as you guys were logging in, your microphones are muted, and that's by default. We want to give our presenters an uninterrupted speaking experience, but we do welcome you guys to interject with questions at any time using the questions module in your GoToWebinar control panel. There will be a section there where you can type in questions. And what we're going to do is we are going to take the questions and answer them sequentially at the end of Dr. Shi's talk. That'll come in about half an hour's time or so. So just send in your questions at any time, and we'll be more than happy to take them there. So it is now the top of the hour, 11 a.m. Pacific, 2 p.m. Eastern. So let me turn things over to Wenqing, and we can get started. Wenqing, you have the floor.
Oh, sure. Thank you, Jared, for the introduction. So good morning, everyone. Good afternoon, good evening, depending on where you are. So I am Wenqing, an application scientist here at Park Systems, and it is my great pleasure to be here today to give this webinar about PinPoint Piezoelectric Force Microscopy, or in short, PFM. So before we get started, I will give you a brief introduction about our company, Park Systems. So Park Systems is a world-leading manufacturer of atomic force microscopes and emerging nanoscale microscopy systems. We develop solutions for many research and industrial applications, enabling advances in science for major universities and national labs, and a wide variety of national companies specialized in diverse fields. As you can see here are some of our representative customers. We have universities like Stanford, Harvard, and major companies like IBM, Toshiba, Samsung, and so forth. So our product line covers just about every usage case with fully manual to fully automated instruments. So as you can see here, we have our research line starting from our XE7, which is a cheaper option and a very economy efficient option. And also we have our NX high-vac system, which can be used under high vacuum conditions. So here are our automated industrial systems. We have our NX HDM all the way up to our NX 3DM. So those are mainly used in product lines for wafer characterization purposes, and they are fully automated. So our AFM technology offers the best accuracy, the highest resolution, and it's the easiest to use on market. So if you are interested and want to learn more about our company, please visit parksystems.com for more information. So without further ado, let's get started. Here is a brief outline for today's presentation. I will first introduce you piezoelectric force microscopy, or PFM, give you the definition of piezoelectricity, and along with some examples. And then I will explain how does PFM work, including lateral PFM and also vertical PFM, and the information they can give us. Then I will introduce another capability of PFM, which is lithography. Next, I will introduce you a novel mode developed by Park Systems, the PinPoint PFM technique. That's the major part of today's presentation. I will show you how it works, And finally, I will show you the experimental results comparing the performance of PinPoint PFM and conventional PFM. And hopefully from today's webinar, you will learn more about this PinPoint PFM technique and why it is better than the conventional contact PFM technique. So let's get started. Piezoelectric material basically converts an applied mechanical force into an electrical signal. So you can find piezoelectric materials around us pretty much every day. Chances are that you have already used some sort of piezoelectric material a few times already for today. For example, you can find piezoelectric material in your car, in the brake systems of your car specifically. So in the tire pressure gauges, for example, when you hit the brake, a mechanical pressure will be applied, and then the piezoelectric material will be responsible of translating this mechanical pressure into an electrical signal, which will signal the computer in your car to eventually break the wheel of your car. Also in microphones and cameras of a smartphone, we will have piezoelectric material, and also in medical imaging like ultrasound. Of course, here at Park Systems, our favorite, the piezoelectric material used for our X, Y, and Z scanner, which is what allowing us to obtain high resolution AFM images. So now let's look at what makes a material piezoelectric. So most piezoelectric materials are crystals, so they have an atomic lattice and stays neutral most of the time. But when you apply a pressure or a piezo, then you can induce a net dipole, which is like small translation of the atoms, causes this net dipole, and then eventually lead to electrical polarization. So piezoelectric materials can also be ferroelectric. Ferroelectric materials exhibit a permanent electrical polarization with applied electrical field. So this is the piezoelectric effect, but this effect is also reversible, and that leads to the inverse piezoelectric effect. So in the inverse piezoelectric effect, you apply a voltage to the material, and then this material will have a mechanical deformation in response to the applied voltage, meaning that after you apply this potential or this bias, the material will contract or stretch out based on the applied bias. And this inverse piezoelectric effect is what we monitor in piezoelectric force microscopy, or in PFM. So these piezoelectric materials have predictable deformation once a bias is applied, and one can use equations to convert the applied electrical voltage to piezoelectric response. And the deformation of the sample is not only predictable, but they tend to be quite small, mostly in the nanometer regime. And also, polycrystalline dielectric materials have discrete piezoelectric domains, and these are on the nanometer and potentially micron size scale. So you can imagine that this can be quite challenging to characterize, because you have nanometer or micron size domains, and then the deformations are very small, mainly on the nanometer regime. And that brings us to atomic force microscopy, AFM, and piezoelectric force microscopy, PFM. Excuse me. So PFM is really a non-destructive technique that have nanometer scale resolution, and it will allow us to characterize this piezoelectric and ferroelectric domains at the nanometer length scale without having to sacrificing your sample, without putting any damage to your sample, ideally. So in PFM, we have 3 channels mainly. Topography channel is very self-explanatory. From the topography channel, what we can learn is like features at our surface, the topography, the morphology. And then we have a PFM phase and a PFM amplitude channel. From the PFM phase channel, we can get the polarization direction. And on the other hand, from the PFM amplitude channel, we can get the physical displacement. So that's about the channels we're looking at in PFM experiment. And right here, I have a Park NX20 system. It's our flagship system. It's a quite compact system that can do not only topography imaging, PFM, and also many advanced modes. So most of the measurement that I will be introducing you today were performed with the NX20 system. So I have it shown here for your reference. Just to give you an idea of how PFM works inside a Park AFM, I have this slide here showing some of the key components of our machine. So we can see how our instrument is able to give us these signals. So I want to point out that this schematic is showing imaging in contact mode. So conventional PFM is typically performed in contact mode. So keep this in mind, because when we talk about pinpoint mode, you will find the difference between the conventional PFM and also the pinpoint PFM. And the image is performed with an electrically conductive tip right here. So the schematic here shows how a topography signal is generated in contact mode, basically. We have a laser that hits the back of the cantilever and is reflected by the back of the cantilever and is directed to a position-sensitive photodiode detector, or the photodiode here. The AFM tip is raster scanned across the sample, and changes in the sample topography produce changes in the laser position on the photodiode. And this signal will pass to a locking amplifier and through a feedback loop, and eventually to our Z piezo to keep the force at the tip sample contact point constant. So this is how we would get topography signal in contact mode, as you can see here, topography or the Z height information. But if we want to get piezoelectric response, we need to have a second locking amplifier, which will allow us to read out the PFM signal, including the phase and also the amplitude. So in PFM experiment, an AC bias is applied to the tip, as you can see here. And if your material is piezoelectric or ferroelectric, it will respond to this applied AC bias. However, this response has a very low signal-to-noise ratio and must be separated from the topography signal to be able to be read out. So Park achieves this by using a second locking amplifier, as you can see here. So a second locking amplifier is connected to the deflection signal to selectively drive the desired AC frequency and bypass the unwanted signals. So PFM phase and amplitude signals are acquired and can provide us the information about the direction of the electrical polarization and also the swing. So to understand how these parameters are acquired, I will next discuss the different modes of PFM. But here is the general schematic of how Park achieves PFM mode. So hopefully you learn how our AFM does PFM, but how about analyzing the data and what does it mean and different ways we can do PFM? So in PFM, there are several different modes. The first that I will describe is the vertical and also lateral PFM modes. The position sensitivity of the photodiode allows PFM to identify the direction of the electrical polarization in active piezoelectric and ferroelectric domains. So in this image shown on this slide, if there's no deflection of the cantilever, the laser spot would stay right here at the center of our photodiode, or the 0, 0 coordinate. So the first mode shown here is vertical PFM, where one can imagine that the laser will deflect vertically as the cantilever deflect up or down in response to the material which is changing as a result of its piezoelectric properties. So vertical PFM provides information about out-of-plane electrical polarization and deformation. Out of plane meaning perpendicular to your sample surface. Okay. So, and then we also have lateral PFM. From its name, it's very obvious that in lateral PFM, we essentially are looking at the lateral rather than the vertical components. As you can see, we are looking at the signal that is parallel to the sample surface. So you can imagine that the material may share in plane parallel to the sample surface. So this information allows us to gather in plane electrical polarization and deformation in the phase and amplitude signals, respectively. This directionality allows PFM to provide information about the directionality of the strain and polarized domains. So now moving on to the representative PFM experiment that I am going to demonstrate today. First, I want to show you how PFM can be used for reading and writing ferroelectric domains using a material called lead zirconic titanate, or PZT film. A little bit about ferroelectric patterning and lithography, as we are going to highlight the ability for PFM to do lithography with the sample. So the surface property of a ferroelectric material depends on the direction of the electric polarization. And domains of the material will essentially be chosen, and you can write into the material to have a desired electrical polarization or desired surface property. So PFM can be used as a tool for ferroelectric lithography to write domains with nanoscale precision without affecting the surface topography. And these domains are then often used to perform subsequent chemical reaction or can provide sites for controlled assembly of functional nanostructures. So here is an example of how a ferroelectric material will behave in response to an applied bias. So we can increase the bias or the voltage above this value to allow for the domains in this case to be directed to point upward like this. Or we can reduce the bias to a voltage that is below this value to achieve a downward electrical polarization. In brief, what we will do is to apply a sufficient positive voltage to allow for one direction of polarization, and then we will pick another region, and we will then orient the electrical polarization in the opposite direction by applying a, say, sufficiently negative bias. So here is a topography image of this lead zirconic titanate, or PZT film. Excuse me. As you can see, there is no specifically noticeable surface features. So we want to perform the experiment and see if we can write on the material, or in other words, alter the electrical polarization direction, and then look at the PFM signal to read it out, read the electrical polarization that we just write on the material. So what we will do is that we will write a domain with 3 micron by 3 microns. To do this, we simply choose a 3 micron by 3 micron scan in the AFM, and then we scan it with the applied positive 10 volt DC bias to the tip. And then we will choose a smaller region, in this case a smaller 1 micron by 1 micron region, and we will put it in the center of the original 3 by 3 micron scan, and then we will apply a negative 10 volt DC bias to the tip for this 1 by 1 micron scan, and we scan it. So this is the writing procedure. To read, we will zoom out to a 6 by 6 micron area, because we want to include all the previous scanned regions, and we want to have some reference point. So we scan a larger region that outside the 3 micron by 3 micron and 1 micron by 1 micron scan. So in this case, we don't apply any DC bias to the tip. So 0 applied DC bias. So eventually, we will have 3 different domains. One being the unbiased one, which is the 6 micron by 6 micron area, and a section of positively biased. That's the 3 micron by 3 micron region, and a section that is negatively biased. That's the smallest 1 micron by 1 micron region. And then we will check the PFM base to see if we can identify those different electrical polarization domains. So PZT films are ferroelectric, and they will hold a permanent electrical polarization state when a voltage is applied. So we should be able to visualize these electrical polarized domains that we just wrote with PFM. So right here, I have the experiment in action, and I'm gonna play and show you what we did. So to start, we input a sample tip bias here from the software, positive 10 volt, and we scan the 3 micron by 3 micron region. So here is the scan. This is a phase channel, so we don't expect to see much. But here is the topography channel, and you can see we monitor the topography and phase separately. And next, we zoom in. In the center of the 3 by 3 micron, we scan a smaller region with negative 10 volt tip bias. This is a 1 micron by 1 micron scan. So finally, to read out 0 watt DC bias applied to the tip, we scan a 6 by 6 micron region. And here is the result. So clearly, we can see that we have 3 different regions, 3 distinct regions of intensity in the PFM phase signal. So just to look at this image once again, this is a PFM phase signal, and you can see that there is a brighter region right here, which corresponds to that 3 by 3 micron scan written with the positive 10 volt tip DC bias. And then in the center, we have the darkest region, that is the 1 micron by 1 micron scan with negative 10 volt applied DC bias to the tip. And then the region outside is our reference region, which has not been influenced by external applied tip bias and remains as randomly oriented domains. So patterns can be read after applying voltages with opposite polarity, showing the anti-parallel out-of-plane strain and electrical polarization. So here, I'm going to show you a very similar but different example. So here, what I did is we first scanned a region that is 6 micron by 6 micron, so the largest region, with negative 10 volt DC bias applied to the tip. And then we scanned a 3 by 3 micron region with positive 10 volt DC bias applied to the tip. And finally, in the center, we scanned a 1 by 1 micron scan with, again, negative 10 volt tip bias, DC bias. So in this case, we would expect that the inside square right here, the 1 micron by 1 micron area, and the outside square right here, the 6 micron by 6 micron area to have the same polarization direction, as they were both scanned with negative 10 volt DC bias applied to the tip. So to check that, we drew a line profile along the face image. The line is right here, and the line profile is shown here. So we observed a 180-degree phase difference between the bright region and the dark region, indicating we have opposite electrical polarization, and we have 0-degree phase difference between the outer dark region, the bigger one, and the inner dark region, indicating there's no, that they have the same electrical polarization property. So we can also look at the PFM amplitude signal. So as I mentioned, PFM amplitude is the deformation of the sample. So here you can see that the bright region in the amplitude corresponds to the dark region in the phase. So hopefully from the last example I showed you, you've got the idea of how conventional PFM works and what kind of information we can get from it. Now I will switch gear and introduce you an advanced PFM technique developed by Park Systems, the PinPoint PFM technique. I will first walk you through how PinPoint PFM works. Next, I will compare the performance of conventional PFM and PinPoint PFM using the images taken in these two modes of a sample that is consisted of a near phenanthrene on ITO surfaces. So basically, I will introduce how PinPoint PFM works, and followed by that, I will show you the images taken with both conventional PFM and also PinPoint PFM. So how does PinPoint PFM work? Basically, in PinPoint PFM mode, the AFM probe monitors its feedback signal, first approaches towards the sample until a predefined force threshold value is reached, and then the Z-scanner position will be measured, which will be our Z height signal, and also the probe will keep in contact with the sample for a certain amount of time that can be defined by the user. This is for the piezoelectric response acquisition, including the PFM phase, PFM amplitude, and also the PFM chord signal. So after the signal acquisition is finished for both the height and the piezoelectric response, the AFM probe will be rapidly retracted away from the surface, again to a user-defined height. And then the XY scanner will move to the next pixel. And then the probe will approach towards the sample again until a predefined set point is reached. And then it will be the Z-scanner position and piezoelectric response acquisition. Again, AFM probe will retract away, XY scanner move to next pixel. So this entire process will repeat over and over until all the pixels within your image are scanned. And in the end, you will get a topography signal along with the piezoelectric response signal images. So PinPoint PFM really allows for higher spatial resolution with optimized piezoelectric response measurement over different sample surfaces. No matter your sample is very flat or very rough, PinPoint PFM will prevent the tip and sample from scratching on your sample. So PinPoint PFM was designed to replace the conventional contact PFM, and it's an enhanced design that eliminates the problem of the tip wearing out during contact mode topography and diminished contact time. So the PinPoint PFM technology has proven to solve majority of the shortcomings of conventional PFM, including quick tip wear, degradation of resolution, no signal-to-noise ratio, and poor reproducibility. Imagine for conventional PFM, since we are doing the experiment in contact mode, so essentially if your sample is very rough, the tip can be scratching on your surface furiously. which will lead to tip wear, of course, and then degradation of your resolution. However, in our PinPoint PFM, the user can define the contact time by depending on their sample. They can tailor all the conditions depending on the sample. So instead of constantly scratching on the sample, the tip and sample contact time is minimized, which will maximize the tip life. So now I'll show you some proof by giving the performance comparison between conventional PFM and PinPoint PFM. So as mentioned previously, the sample we use in this case is phenethering on ITO surfaces. So here are the imaging conditions. In both PinPoint mode and in both PinPoint PFM mode and conventional PFM mode, the scan size was set to 20 by 20 micron, and a AC potential with an amplitude of 4.5 volt and a frequency of 17 kilohertz was applied to the tip, and no DC potential was applied to the sample. So in PinPoint PFM imaging, we used a PPP EFM cantilever, which has a nominal spring constant of about 2.8 Newton per meter, and this cantilever was coated with platinum to ensure its conductivity. And the nominal radius of the tip curvature is about 25 nanometer, and the force set point used in this case is about 196.8 nanonewton. The retract height was 0.3 micron. If you remember that when I explained the PinPoint mechanism, the probe will retract away from the surface to a safe height, a user-defined height, prior to moving to next pixel. So this is the retract height. We have 0.3 micron here. And the retract approach speed is set at 20 micron per second. And the contact time between the probe and the sample surface was controlled at 1 millisecond. And again, this value can be adjusted or tailored to the sample as needed. So in conventional PFM imaging, we used a NSC36 cantilever, which has a nominal spring constant of 0.6 Newton per meter, and this is coated with chromium and gold. The nominal radius is also 25 nanometer, and the scan rate was 0.2 hertz. So I want to mention that for conventional PFM measurement, our initial attempt was to use the same cantilever, the PPP EFM, which is what we use for the PinPoint PFM measurement. However, this probe was constantly scratching on the surface, and the imaging quality was not ideal. And thus, we used a cantilever with smaller force constant, as you see here, the NSC36C, in hope to kind of elevate this scratching on the surface problem. Albeit that this NSC36C cantilever has a much smaller force constant compared to the PPP EFM, the probe was still dragging on the surface and resulted in imaging artifacts in conventional PFM. So that's I want to show you the image in the next slide, so you can kind of have an idea of what do I mean by scratching on the surface. So here is an overview of the performance comparison. On the left-hand side, we have the images for conventional PFM right here. We have the height on top and the PFM signal on the bottom. And on the right-hand side, we have the PinPoint PFM signal, where topography we have on the top and the PFM signal on the bottom. At the first glance, we can tell that the images collected by the PinPoint PFM definitely has better quality compared to that collected by conventional PFM. So let's take a closer look at the topography data. From the topography images, the annealed phenethering polymer was resolved under both imaging conditions, and they were observed to be like rod-shaped features with pointy ends. like the features right here, right here. So the height of the polymer rod was measured to be ranging from tens to hundreds of nanometers, while the width of the polymer rods was measured to be between several hundred of nanometers to a couple of microns. So it is noteworthy that the quality of the topography image obtained by PinPoint PFM is improved compared to that taken with the conventional PFM. From the conventional PFM imaging conditions, imaging artifacts can be seen throughout the entire scan area, indicating that the probe was kind of scratching and dragging on the sample. We have distorted topography, and accurate dimension measurement of the features was very difficult, nearly impossible. So to give you an example, here we draw a line profile along the red line, and here is the actual line profile. If we want to measure the width of the rod or the length of the rod, so here is what we measure, 5.6 micron, which is obviously not the actual length of the rod, but kind of the indication of the probe is dragging on the sample. So that is not an accurate measurement. On the other hand, under the PinPoint imaging conditions, the annealed phenanthrene polymer were well distinguished from the ideal substrate, and dimension measurement can be made easily. For instance, here we have a rod that's 0.817 micron in width and about 234 nanometer in height, as you can see here. So the reason why we have better results with PinPoint PFM is that the probe was retracted far away from the surface to a safe height at every pixel prior to approaching towards the surface again. And the scratching between the probe and the underlying substrate was then effectively eliminated, leading to significantly improved imaging quality. Similar results were observed in the piezoelectric response images. So by comparing the results of the two techniques, one can easily determine that the PinPoint PFM has better performance. So if you look at the conventional PFM image, here we have a line profile along this red line drawn in the image. We have two huge spikes in the line profile, indicating that the probe is again scratching on the sample. On the other hand, with the PinPoint PFM, we have no overshoot in the PinPoint PFM PFM signal, indicating that the probe is not scratching on the surface. So finally, I want to show you another capability of PFM, that is switching spectroscopy. So in this technique, you can monitor the PFM amplitude or the PFM phase while sweeping the applied bias. The resulted hysteresis curve can provide localized information with respect to the switching properties of the piezoelectric material that we're looking at. So on the left, we have an example of an ideal system's PFM amplitude or strain response during a voltage sweep. So you can see that as you increase the bias, you have strain, and then as you decrease bias, it flips. Similarly, for polarization, the ideal system's response to sweeping voltage is shown here on the right. For the PFM phase, as you sweep up and sweep back down the bias, you can see distinct flipping. So here we have a term EC, which is the coercive voltage. So that is the voltage at which the flipping occurs. The coercive voltage is a measure of the ability of a material to withstand an external electric field without depolarization. And the value can be determined from this PFM phase plot. So you can see in the schematic where we have random orientation of polarization directions before they take a predominant direction. So spectroscopy can be really performed at specific regions of interest, and from which we can learn about the fatigue and performance of the device at nanoscale. So here is the example of switching spectroscopy. In the red star here shows the location where the switching spectroscopy was performed. And here are the results of the switching spectroscopy. So we swept the bias from 0 to positive 1.5 volt, and then from positive 1.5 volt back to negative 1.5 volt, and finally back to 0 volt again. So on the left, we have the PFM amplitude response. Since the PFM amplitude directly measures displacement of the sample, the strain response as a function of the sample bias can be measured in a specific piezoelectric domain. And this curve has a characteristic butterfly shape for piezoelectric materials. In addition, we can learn the coercive voltage from the curve. It's about 0.3 volt. On the right-hand side, we have the phase hysteresis loop, which is a typical response of the ferroelectric material. So in conclusion, the PFM spectroscopy enables analysis of structure-function relationships and device performance assessments. So with that, I would like to conclude my talk and briefly summarize what we've gone over today. First, representative PFM experiment that I showed you today is writing and reading ferroelectric domains with a lead laconic titanate or PZT film. We went over how to do lithography with PFM and also how to write and then read ferroelectric domains with PFM. And then the main take-home point of today's webinar is the performance comparison of conventional PFM and PinPoint PFM. By comparing both the topography and the PFM response images of the phenanthrene film annealed on ITO, the advantages of PinPoint PFM over conventional PFM is very clear. The PinPoint PFM mode introduced by Park Systems has proven to offer significantly improved quality in both topography and piezoelectric response measurement. The advanced PinPoint mechanism eliminated the frictional force between the probe and the substrate, enabling concurrent high-resolution topography and piezoelectric response mapping. In addition, the response in strain and polarization as a function of applied voltage was also examined to obtain insights regarding material characteristics such as coercive voltage and hysteresis. So taken in total, PinPoint PFM mode is the ideal approach to characterize localized piezoelectric response at nanoscale with maximized tip life and sample originality as a result of this minimized frictional force between the tip and the sample. So with that, I'd like to thank you all for your attention, and I'm happy to take any questions.
All right. Thank you very much, Wenqing, for the talk on PinPoint PFM today. Before we go ahead and go into the questions that have been submitted, let's see here. There's a couple of items that I wanted to announce. So, as mentioned on the last slide here from Wenqing's stack, the website for Park Systems has changed. In the past, you might remember Park Systems being parkafm.com. It is now parksystems.com. If you have your old bookmark still set to parkafm.com, don't worry. They will redirect to the new website address. So there you go. And also, like I mentioned at the top of the session today, the talk that you just listened to, as well as all of the previous webinars that have been given by our guest presenters in the last 3 to 4 years, are all archived on the Park Systems YouTube channel. The URL for that is youtube.com/user/parknano. I have dropped that web address into the chat. So if you guys want to follow that in your web browser, and then of course subscribe to the channel for updates, you are more than welcome to do so. So with that, let's see here. We do have a couple of questions in queue. The first question for you, Wenqing, reads, can you calculate the piezoelectric coefficient, D33 for example, after you do the domain writing? If so, how?
Yes, yeah, we can calculate the D33 factor, and the calculation procedure is a little bit long and complicated. So if you're interested, please send us an email to techsupport@parksystems.com. We will reply you. We have PowerPoint procedure of how to calculate the D33, so we will send it to you if needed.
Okay, very good. I will go ahead and put that email address, techsupport@parksystems.com, in the chat. Like Wenqing mentioned, please feel free to write in for more information on that calculation procedure.
And also, I will put my email address also here in the chat. So if you want to email me directly with the procedure, asking for the procedure, please do so. Thanks.
That's right. Oh, Wenqing, can you retype that and then send it to the entire audience? It looks like you sent it to organizers and panelists only.
I see. Okay, let me do it again.
Cool. Okay, so while she does that, let's go to the next question in the queue. The second question reads, how much does the PinPoint version of PinPoint PFM, how much time does it require to complete a scan compared to, say, conventional PFM?
It actually doesn't take much longer, but I would say it's long because if you imagine for the conventional one, we use 0.2 hertz, which will be 20 minutes or 30 minutes for each scan. So PinPoint will give you better result in around the same time, 20 minutes or something like that. Yeah, because in PinPoint mode, imagine the probe need to hop down and hop up, move to next pixel. So this hopping process takes time. And also sometimes you might need to keep the probe in contact with the sample for a longer time to achieve better piezoelectric response. So that will also take longer time. But for the images I've showed you, around 20-30 minutes will give you the PinPoint PFM images.
Great. Thank you for the insight, Wenqing. Let's see, the questions keep coming in. Our third question from the audience says, can PinPoint PFM be used for biological samples?
Yes, I think it can. For biological samples, you just need a much softer probe. So we use 2.8 Newton per meter and also 0.6 Newton per meter. I would imagine that for biological samples, you might need cantilevers that are 0.05 Newton per meter or something like that. And then you can do PFM. And also you need to take consideration that some biological samples cannot withstand a high tip bias. And also you might not want to apply any DC bias to the sample because that will maybe kill the cell or something. But if you have alternating AC bias and a small enough AC bias, I think you can do PinPoint PFM on biological samples.
Excellent. All right, our next question, oops, let's get back up there. Okay, our next question reads, is application of voltage necessary during PinPoint mode?
Application of the AC bias to the tip is necessary, but DC bias to the sample is not necessary.
Thanks for clarifying that. Let's see here. Next question says, in regards to older Park Systems AFM models like the Park NX20, for example, are they capable of being configured to use PinPoint PFM?
That I need to check with our factory. It is possible, For XC70 system, yeah, I think it is possible. You just need some maybe like software patch or something to enable the pinpoint mode. But I need to check with factory. So if you are interested, please send us the email and we will follow up with you.
That's right. And that's a good reminder. I went ahead and typed in addition
Great.
to Wenxing's email address, also there's the tech support, the general tech support email address for the team here. And if you have questions about making PinPoint PFM operational on older models, feel free to drop us a line there. We'll be happy to follow up with you directly. Okay, a lot of engagement from the audience here, a lot of interest. So we still have a couple more questions here, Wenxing.
Sure.
The next one reads, how is the PPP EFM tip different than, let's say, typical EFM tips like Multi-75E or NCST Gold? Have you used those?
Let me check. Let me check really quick. So this PPP EFM tip, it's from nanosensors, and resonance frequency is about 25 kilohertz, and it is coated with platinum on both the front and back side. I think it's just a regular cantilever, because for pinpoint mode, it's not necessarily, you don't need a like special cantilever. You can use like any cantilever. So I think this is just like came handy and we have it, so we use this one for the pinpoint measurement.
Right. And in addition to that, yeah, just as a note for folks, Park does source tips from the cantilever manufacturers directly. So if you have any super technical questions about the cantilever, we do recommend going to the probe fabricator directly, like Nanosensors or Micromash, and inquiring with them. They might know a little bit more than we do if it's specifically about the probe. The next question here reads, can you pull/write sample domains using PinPoint EFM?
With writing, I think you can, but I doubt the effect will be better than just directly writing with contact mode. I mean, yeah, I think with pinpoint you can still do it, but it will be like you have to approach your tip to the sample and keep it there for a while to alter the domain at that specific pixel, and then retract, move to next one. So I think it's like extra hassle to write in pinpoint mode. So I would recommend do the writing or lithography in conventional like contact mode.
Okay, very good. And it looks like we have one more question in the queue, and it reads, and how can I decide on what cantilever to use for pinpoint mode? Do you have any suggestions, I guess?
Yeah, so that will largely depend on your sample. You have to have a cantilever. Like if you have a very soft sample, then imagine if you have a very steep cantilever, you will not be able to get like accurate measurement, and you might end up damaging your sample because the force applied to the sample might be too large. On the other hand, if you have a sample that's very hard, if you have a very soft cantilever that you are using for the pinpoint mode, then you might not get the accurate like measurement because your sample might be like not be able to pushing down your tip might not be pushing down the sample enough. So that's more for like a general pinpoint mode like question. Yeah, so you have to decide, you have to have kind of an idea estimation of your samples, like how hard it is, and then choose the tip accordingly.
Excellent. Thank you for the insight, Wenxing. With that, we have exhausted the queue of questions that are currently typed in. If you have any last-minute questions, we do still have a little time left in the session. Otherwise, we will go ahead with closing. Before I do so, before we close the session here, I just wanted to let everyone know Next month, our webinar series will return to having Dr. Rigoberto Advincula, Professor of Macromolecular Science and Engineering at Case Western Reserve University in Ohio, here in the US. He will be giving a talk, I believe it's going to be the last of his 3D printing series. He's going to be focusing on polyurethane polymers. So if you are interested in additive manufacturing, in the nanoscience behind polymer formation and fabrication for that particular manufacturing method and the industries associated with it, feel free to drop in next month. It should be the second week of June. Details will be up on parksystems.com shortly, in probably around a week or so. So with that, let's see here. One last question. We'll take one more question for today.
Sure.
Let's see here. It says, you mentioned the need for a lock-in amplifier to decouple the amplitude and phase response from the signal noise. So what considerations do you have to make when performing PFM measurements regarding the lock-in amplifier?
Yeah, so basically for this PFM measurement, we need two locking because the first locking was used to lock in to the resonance frequency of the cantilever, or to get us the information of the topography. And then the second locking, because the PFM amplitude and phase signal are quite small, so we lock the second locking to the AC bias frequency. For example, in this case, we use 17 kilohertz as our AC bias frequency. So the second locking is specifically locked at this frequency. So we only pick up the signals from this 17 kilohertz for the phase and amplitude both. So in this way, we have the improved signal to noise ratio.
All right, so that was our last question for today. Do you have any closing thoughts, Wenqing?
Yeah, just if you have any further questions regarding how to enable PinPoint PFM and also like how to calculate D33, those kind of questions, please send us emails so we can follow up with you to help you. Yeah, that's all. Thank you all for your attention.
Excellent. Thank you, everybody. On behalf of Wenqing and everyone else here at Park Systems, thank you for attending today's session. If you have any further questions, either product or technology-wise, or any questions about future materials to be presented in other webinar series, please just visit parksystems.com, drop us a line, and we'll be more than happy to help you out. Until next time, everybody, have a great day and take care. We'll see you in the future soon. Bye.